Welcome to Unit 6, Lesson 3, Composite Functions. Today we're going to be doing something a little bit different than adding, subtracting, dividing, or multiplying, but the basic functions are still going to be there. You just need to understand a little bit of a trick with what we're doing with this composite functions idea, and once you understand it, it's going to be really simple. So a composite function, the composition of f and g of x is defined as f of g of x and is formed when the equation of g of x is substituted into the equation of f of x. So what this is really saying is that you're inserting the function g in the x values of the function f. It's nothing more than that. So it's not the same as multiplying. What we're saying here is that the function g of x, whatever it equals, is going to replace all the x's in f of x. So f of g of x exists only for those x in the domain of g for which g of x is in the domain of f. That's a little bit confusing, but you'll see in the examples what that means. F of g of x is read as f of g of x or f at g of x or f composed with g. So those are three ways of saying the exact same thing. We can write it one of these two ways, f of g of x. Notice that the symbol in the middle here is not a multiply symbol, it's an empty circle. It's another way to write this. So instead of having f of x, we've replaced that x with the value of g of x. Okay? So composition of functions must not be confused with multiplications. That is, f of g of x does not mean f times g. And that's really, really important to remember here. So wherever you see this g of x inserted into the value of f of x, it tells you to do something a little bit different. We have some ways to figure out these problems. So method number one, evaluate the composite function. If f of x is equal to 4x and g of x is equal to x plus 6 and h of x is equal to x squared, determine each value. F of g of 3. So what this is saying is when the function g of x, we've plugged the value of 3 into this, and then the result of that is plugged into f of x. So step number one, determine g of 3. So g of x is equal to x plus 6. When x equals 3, y equals 9. Now that we have that 9, you're going to substitute that 9 into f of x. So f of g of 3 is equal to f of 9. And we remember that f of x is 4x. And wherever there's an x, we're going to put the value of g of 3. Which is 9. 4 times 9 gives us 36. So there's not really a ton of extra work. You just have to remember to insert that function wherever there's an x in f of x. Now, the other thing that we can do is solve the composite function first and then substitute the value in. So we have f of g of x. What we're saying is f of x plus 6, because that's what g of x is equal to. And then figure it out, 4, and then wherever there's an x in f of x, we put x plus 6. 4 times x is 4x. 4 times 6 is 24. Once you have this formula, then you can take that value of 3 that was given and substitute the value 3 in. 4 times 3 is of course 12 plus 24 gives us 36. Notice that method 1 and method 2 give you the exact same answer. It just depends which one you prefer. I prefer this one. I feel like that's easier to not have to manipulate variables. Just solve for the value and then insert that value into the f function. But whatever you prefer, whichever one works best for you, go with that one and use it. The second example, g of h at the value of -2. So first determine h is -2 and then g of h of -2. So h of x is equal to x squared. So when x equals -2 in h of x, then we have -2 squared, which is 4. Once we have this value 4, we just substitute that into g of x. So if you recall, g of x was x plus 6. And so what we're going to do is just take this 4 and put it wherever there's an x in g of x. So our result of g of h -2 is equal to 10. And then the last little part here, determine h of x and then evaluate. So we have h of x. We know that h of x is x squared, so h of x squared. So we're going to take that x squared and plug it in wherever there's an x value. So we will get x squared squared, which is x to the 4th. And it's asking us to fill in the value of 2. So once we have this x to the 4th, all we do is plug in the 2 there. 2 to the power of 4 is, of course, 16. So that's basically it for how you do these problems, but we do need to consider that sometimes there's restrictions on the domain, and we need to look for those undefined values if they do exist. We have a different function here. We have f of x is equal to root x minus 1, and g of x is equal to x squared. So in part A, I'd like you to determine f of g of x and g of f of x, and then determine the domain of all of those functions. So f of g of x, so we're going to take g of x and plug it in wherever there's an x in f of x. So you can see here we have an x here. We're going to take this x squared and plug it in there. It replaces that value. So we'll get x squared minus 1, the square root of x squared minus 1. In the second part, g of f of x, we are going to take root x minus 1 and plug it into the x squared. So if you look at the top here, we have g of x is equal to x squared. This is going to become root x minus 1. So we'll get root x minus 1 squared. And of course, when you square a square root symbol, all that does is just make the square root symbol go away. So g of f of x is equal to x minus 1, or would give us a straight line. In this circumstance, you can see that the order matters because they are different functions. If we're inserting g of x into f of x, we get this result, and vice versa, we get this result. So therefore, the two of them are not equal to each other. When we talk about the domain of the functions, the domain of f of x is x must be greater than or equal to 1, of course, because you can't have 0 under the radicand, and x is an element of the reals. The domain of g of x, it's just a parabola, so x is any x value negative infinity to positive infinity. Then it gets a little bit trickier here once we deal with the restrictions. So the domain of f of g of x is the set of all values of x in the domain of g. So don't forget we're looking at this first. This is what we're talking about right now. That's equivalent to this one here, for which g of x is in the domain of f. So any restrictions on the inner function, this is the inner function, as well as the composite function, so the resulting function, must be taken into consideration. G of x does not have any restrictions on the domain. It's negative to positive infinity. However, when we get f of g of x, and if we look up here at the resulting formula, x squared minus 1 square root, we know that the domain is going to fall between positive and -1. There will be no defined values. So x is less than or equal to -1, or x is greater than or equal to +1. So what we do is just combine the restrictions and give the domain of f of g of x. So our domain becomes x is less than or equal to -1, or x is greater than or equal to +1. X is an element of the reals. In the second part here, we're talking about g of f of x. Now, we want to look at f of x and think, is there any restriction in that function? Remember that f of x is equal to root x minus 1. So, of course, we know that x must be greater than or equal to 1 to give us a value that's larger than 0. So that's a restriction on the domain in f of x. So once we get our composite function here, we know that there's no restrictions on x minus 1. G of f of x is x minus 1. That's just a straight line with a y-intercept of minus 1. There's no restriction there. It goes negative to positive infinity. However, with f of x, it must be greater than or equal to positive 1. So you just state that in your domain. Another thing that you might be asked to do is to determine the composition of two functions and then graph it. So we have f of x is equal to x plus 1 and g of x is equal to x squared, and we'll just go through some examples here. So f of g of x, so wherever there's an x in f of x, we're going to plug in that value x squared. So we're going to get x squared plus 1. F of g of x is x squared plus 1. So we just get this formula for this parabola. It's got a vertical shift up 1 unit, and then it's just a regular parabola shape where the vertex is at 0, 1. The domain, of course, is all real numbers, and then our range has to be greater than or equal to positive 1. We have g of f of x, so they've just swapped places. So now wherever there's an x in the function g, we're going to replace that value of f of x. So f of x is equal to x plus 1. In g of x, we have x plus 1 squared. Now don't forget that this is using your FOIL method. This is x plus 1 times x plus 1. And that is going to give you x squared plus 2x plus 1. When you graph this, you get a parabola that has a horizontal shift to the left 1 unit. And it opens upwards because it's a positive x squared value. So our domain is x is an element of the reals, and our range y must just be greater than 0. Example C, f of x. So wherever there's an x in f of x, we're going to replace it with f of x. A little bit of a tongue twister, but don't think too much of it. Just find the value of this, put it in the x's of the function. So f of x plus 1, wherever there's an x, you're going to plug in x plus 1. So we're going to get x plus 1, and that will give us the straight line x plus 2. Our domain and range in this circumstance are negative infinity to positive infinity. And of course, this is just a straight line graph. In the last example, g of x, so wherever there's an x in the function g of x, you're going to place the x squared. So we're going to get x squared squared. And the resulting graph will be x to the 4th. And you can just pick some mapping points here if you're not sure what the shape of that graph would look like with no other terms attached to it. But basically, it's going to be a kind of flattened parabola. So here our range, y must be greater than or equal to 0. X is an element of the reals, or negative infinity to positive infinity. So don't overthink these problems. You're just taking the value of that function and plugging it in wherever there's an x in the other function, in the original function. So wherever there's an x in g of x, you're plugging in this value. Don't overcomplicate it. Don't overthink it. Just keep it simple. Sometimes you might be given h of x and asked to determine the originating functions. So in the first example, h of x is equal to x minus 2 squared plus x minus 2 plus 1. So in this case, the inner function is g of x and the outer function is f of x. So in A, look for the function that might be common to more than one term in h of x. The same expression, x minus 2, occurs in 2 terms. So we have that repetition here. Try to think of this as a squared plus bx plus c, that that general formula. Once you have that, you can see kind of where some of these terms come from. So if you kind of break it down, you will get g of x squared plus gx plus 1. And then you're just replacing the values. F of x is equal to x squared plus x plus 1. So we know that g of x is x minus 2, and f of x is x squared plus x plus 1. You're basically just factoring. The same thing in the second example, we're looking for the root functions of h of x. We're looking for g of x and f of x. So g of x is equal to x cubed plus 1. So we'll say what's under the radicand will equal to g of x. And then we're just going to work backward to solve for f of x. So if h of x is equal to root x cubed plus 1, and we know that g of x falls under the radicand, then we know that f of x must be equal to root x. So when you get to the end of this, you'll have the two functions. F of x is equal to root x, and g of x is equal to x cubed plus 1. Now, don't overthink this part of it. All you're really looking at here is that this value is being plugged into this x value. So very basically, f of x is root x, and g of x is x cubed plus 1, and it's just being plugged into the value of x. Because remember that the composition of two functions means that h of x is composed of, or made up of, inserting g of x into f of x in this circumstance. Beyond this, you have some practice questions, and once you're done that, you can move on to the homework for this lesson.